Good morning. Contour integration assignment 8. This is very important and expected one. Let's revise some of the few remarks which are important. Let z is r e the power iota theta. Then what is log of z? This will be log of r e the power iota theta. And then this can be written as log of r plus log of e the power iota theta. Very fine. And then this is equal to log of, can I write r as mod of z? Yes, because I know that z is what, x plus iota y, and if I take the mod, this will be x square plus y square under the root, and this is taken to be as r, right? And then this is log of e the power iota theta is iota theta, where theta is the argument. So this is log of mod z plus iota. Can I write argument of z here? Yes. Now what is the real part of log z? The real part of log z is, yes, log of mod z. And the imaginary part of log z is, yes, argument of z. Till now it is clear? Alright. Next. Whatever exercises we have done earlier, in the numerator we are having sine of mx or cosine of mx, right? And then we changed sine of mx to e the power iota mz, cos of mx to e the power iota mz, right? And if there is sine of ax or cos of ax in the numerator, then this will change into sine of az, because here m is equal to a. And then alright, let's read this first. If m is equal to 1, then sine of x, because if m is 1, then this can be changed into sine of x or cos of x. So this will be changed into e the power iota z, because m is equal to 1 over here, right? We have done this, right? Alright, now in this type of assignment, we are going to do work with logarithm, right? So here in the numerator, in the integration, in the numerator, we will be getting log of 1 plus x square. So this thing will be changed into log of z plus iota. Please remember this. Important to remember this, that whenever in the numerator log of 1 plus x square comes, then you have to change this into log of z plus iota. When I do this example, when I do the proof for this example, such kind of examples, then you will get to know why this is changed into log of z plus iota, right? So now I'm going to start with the example having log in the numerator. Alright, fine. The example is, prove that integration from 0 to infinity log of 1 plus x square over 1 plus x square dx is equal to pi log 2. Now here in the numerator I am having log of 1 plus x square, right? So we will integrate fz is equal to as, yes, in the numerator this will be changed into log of z plus iota, right? Sorry. And in the denominator this is 1 plus z square along the contour C, and here this is your contour along the real axis, and then along the semicircle tau, that is mod of z is equal to r, right? And if I take any point on this contour, then this is your argument theta, making the angle with the real axis. Alright, again our first step is to find out the poles. So to find out the poles, I'm taking the denominator equal to 0. So 1 plus z square is equal to 0. And then z is equal to, clearly z is equal to plus minus iota, very good, of which will lie inside the contour only. Z is equal to iota lies inside C, the contour C, right? Now I am going to find out the residue at this iota, right? And the formula for that is log of numerator as it is, and then we take the derivative of the denominator with respect to z at z is equal to iota, right? And this is equal to log of, now at z this will be 2 iota over the derivative is twice of z, and then twice of z is iota, so I'm writing 2 iota again. So this is your residue. Fine, all right. Now third step is I have to use the Cauchy residue theorem, and the integration over C fz dz is equal to 2 pi iota times the residue. This is the Cauchy residue theorem. So this is 2 pi iota times, what is the residue? The residue is log of 2 iota over 2 iota, right? And this will this 2 iota will be cancelled out, and I'm lefting up with pi log of 2 iota. Is this clear? All right. Now I'm going to split this C in first along the real axis, negative r to positive r, and writing here f of x dx, and then along the semicircle tau, and here it should be f of z dz. This is equal to pi. All right. Now what is log of 2 iota? Just now in the remark we have read that this is changed into, yes, log of mod of 2 iota, yes, plus iota times argument of z. Here z is 2 iota. If we are focusing on the formula then, right? So this is equal to pi log of, I know that mod of iota is 1 always. Let me write here, note mod of iota is equal to 1. The proof for this has been done in the earlier videos. So this is log of 2 plus iota. Now argument of 2 iota, this is what this is, pi by 2. I have explained all these things in my series of stereographic projections. There you can read all the examples and exercises based on such arguments and the principal values, right? You can check over there. Just go through those assignments. You will get to know how to find out this. And then this, now this will always comes out to be 0, but in case of log, how is this possible? That is now I'm going to explain, which is pretty much lengthier. Alright, so this is integral over tau f of z dz. This mod is equal to mod of integral tau log of z plus iota over z square plus 1. This is our f of z function. This mod is, alright, now what is my z? It is r e the power iota theta. Here I am taking the capital R because I have used capital R in the integration. And this is z is r e the power iota theta on tau. And what will be your dz? This is r e the power iota theta into iota d theta. Fine? Alright. And what is the angle made by this tau? It is from 0 to pi, right? Look over here, from 0 to pi. So next, this is equal to, for tau, I'm writing the limits from 0 to pi, log of, instead of z plus iota, I'm writing the value of z here, r e the power iota theta plus iota. Please look carefully every step. This is r square e the power 2 iota theta plus 1. And then for dz I am writing r e the power iota theta into iota d theta. Right? Okay. Next step is mod 0 to pi. Alright, this is log of r e the power iota theta into 1 plus 1 over r e the power iota theta, because I have taken r the e the power iota theta outside, and this will be then iota over r e the power iota theta, right? Over denominator as it is, and this is r e the power iota theta into iota d theta. Fine, mod is going along with every step, so this is equal to now. Now what I'm going to do is, I know that log of a into b is log of a plus log of b. So 0 to pi log of r e the power iota theta plus log of this 1 plus iota over r e the power iota theta. So log of 1 plus iota over r, and e the power iota theta I am taking to the numerator, which is negative iota theta, right? And then this is r e the power iota theta into iota d theta, and denominator as it is. Fine, okay. So in the next step, what I'm going to use is, again, here I'm having this product r into e the power iota theta. Let me also change this as 0 to pi log of r plus log of e the power iota theta, right? Log of e the power iota theta. And then this is plus log of 1 plus iota e the power negative iota theta over r, bracket close, r e the power iota theta into iota d theta, and then the denominator r square e the power 2 iota theta plus 1 with mod. Now I know that the inequality that mod of a plus b is always less than equal to mod of a plus mod of b. So I'm going to use this in the numerator, right? So this is okay, now the sign will be less than equal to, because I'm using the formula for the inequality, mod 0 to pi, and this is log of r plus log of e the power iota theta will be iota theta plus log of 1 plus iota e the power negative iota theta over r, and then again mod r e the power iota theta into iota. Everywhere there is mod now. Mod of r square e the power 2 iota theta plus 1. I have not used right now that formula, because first I am taking the mod everywhere, with everyone I am taking the mod, Now I am going to, because this is also less than equal to separate mod, right? Now I am going to use that mod of a plus b is less than equal to mod of a plus mod of b. Okay, because now this mod is, there is no mod because I'm using the formula now. So this is just the integration 0 to pi. This complete mod, right? So this will be changed into, yes, log of r plus, what is the mod of iota theta? This is theta because log of iota is, sorry, mod of iota is 1. I'm extremely sorry. So I have just taken this mod of this plus mod of this. And mod of iota is 1 and mod of e the power iota theta is also 1. So here only r is there over. Now this is because now the mod is in the denominator, so that is 1 over mod of a plus b, that is less than equal to 1 over mod of a minus mod of b. So mod of a, this is r square minus this is already 1, right? And then this is further equal to 0 to pi. This r over r square minus 1 I'm taking outside, and the bracket log of r plus theta, and then this modulus log of 1 plus iota e the power negative iota theta, sorry, over r mod d theta. Now this is less than equal to, now I'm using the maximum value of theta over here and over here. Now here theta is increasing function, so the maximum value for this theta is pi, right? So this is 0 to pi r over r square minus 1. This is log of r plus pi. Obviously this term will be greater than the previous one, plus this is log of, now e the power negative iota theta is decreasing function, and whenever there is a decreasing function, that function will be maximum at the lower limit. And what is the lower limit? That is 0. So to maximize the decreasing function, I have to use a lower limit over here. So this is 1 plus iota. Now e the power negative iota, this is 0, that means e the power 0, which is equal to 1. Then this is d theta. After that, this is equal to, okay, just multiply this r with log of r. Just watch this, the complete function. This is r log of r over r square minus 1 plus r. Now there is no theta here, so the integral will be theta, right? So this is pi times this thing. So this is r over r square minus 1 complete bracket log of 1 plus iota over r. Now this, the integration will become this. Now this thing is tending to 0 as r is tending to infinity, because Jordan's lemma needs r needs to be tending to infinity for Jordan's lemma. So as r tending to infinity, this whole thing is tending to 0, which means our integration is tending to 0, which means the second term, the second integral, this, I have proved that this is tending to 0. Fine? Or this thing is tending to 0. So we have left with only this. So the limit r tends to infinity mod of integration along tau fz dz is less than equal to 0 because the sign is less than equal to, right? So whenever the integration mod is less than equal to 0, which means it is also, this implies that limit r tends to infinity mod of this integration tau fz dz is equal to 0, which implies limit r tends to infinity integral over tau fz dz is equal to 0. For this, I need my r to be tending to infinity. Now let's check our statement 1. In this statement, let me write this as, mark this as statement 1. In this statement, I'm going to let r tending to infinity. When I'm going to let r tends to infinity, this second integration will be tending to 0, which we have just now proved. So just writing here that letting r tends to infinity in 1, we get, okay, minus infinity to infinity because I'm having negative r to positive r, f of x dx. Second term, second will be 0. Second integral will be 0. So this is pi log of 2 plus iota pi by 2. What is my function? The function is log of x plus iota over x squared plus 1 dx. So this is equal to pi log of 2 plus taking pi inside. So this is iota pi square by 2. And then this is equal to minus infinity to infinity log of x plus iota. The formula is mod of x plus iota plus iota times the argument of this z, which is x plus iota. Again, I'm saying here, according to the formula, I'm using this x plus iota to be a z. You can replace that with any other variable in which you are comfortable. So just for the formula, I have said that this is log of mod of z plus iota argument of z, where z here for this formula is x plus iota. So over x squared plus 1 dx is equal to pi log of 2 plus iota pi square by 2. Now I need to equate real part or imaginary part. For this, you need to check your integration. So let's go back. I need pi log 2, right? So here, because I need pi log 2, so now let me check. Where is pi log 2? Pi log 2. And this is your imaginary part or real part? This is real part. So I am going to equate the real part, right? So equating the real part, I get, I'm writing pi log 2 first. So this is equal to minus infinity to infinity log of x plus iota over, of course I'm not going to write this, x squared plus 1 dx. So this is equal to minus infinity to infinity because I'm very much know that this mod of x plus iota is nothing but square root of x squared plus 1. That is why, right? Okay, so this is equal to, now this is minus infinity to infinity log of this square root, and I know that square root can come out as 1 by 2 fraction because here it is log as a power. This is the rule that power will go to the backside of the log. So this is half of log x square plus 1, and I have taken this half to be outside of the integral, and this is x square plus 1 dx. Now, is this my even function or odd function? Yes, this is your even function, completely even function. So this can be written as twice 0 to infinity. So now can I write this on the left hand side? Thank you. So this is 0 to infinity. Already half is outside, and this is twice. Wait. Twice should be also outside. Twice 0 to infinity log of x square plus 1 over 1 plus x square, or x square plus 1. Dx is equal to pi log of 2, and 2 and 2 will cancel out. So this is finally 0 to infinity log of x square plus 1 over x square plus 1 dx is equal to pi log 2. So easy to understand, so easy to understand. Thank you so much, friends, for watching this video. Please do revise all the steps. These are very easier, and do subscribe and this channel for the latest videos. Thank you so much. Goodbye. God bless you.